I'm Fernando Pereira, and today I will explain you how we can solve a constraint system with conditional constraints. We can easily visualize a constraint system as a graph. Vertices represent either labels or variables, that is, the indices of the cache and the environment. In conditional constraints, add edges to the graph. If P is in Q, then we have an edge from P to Q. Conditional constraints add what we call candidate edges. These are edges that will become real once the condition is met. So here's the graph for our example system. We have 6 vertices, 4 representing labels and 2 representing variables. Let me enlarge the image so that you can better see the graph. Maybe you could stop the video and try to figure out why we have such and such edges and what are the candidate edges. We shall be associating each vertex with a value set. The value set contains the functions that can be stored in that variable or label. The goal of the algorithm is to find all the value sets in every vertex. We have value sets for the constraints that contain constants on the left side. In this example, we have 2 such constraints. Then we will add fn of x is x to the value set of C2 and fn of y is y to the value set of C4. Just to avoid having to say fn of x is x all the time, I will call this function idx. The same goes for the other function. I will call it idy. Now we need to solve the constraint system. We will adopt the lemmings model. Lemmings are those small kind of mice that reproduce like no tomorrow and that migrate in the Arctic once there are too many of them in a region. I say lemmings model because we shall be migrating constraints all over. Whenever we have an edge from x to y, then all the functions from x also go to y. We replicate them so solid edges are like slides. All the functions in the origin sort of slide down to the destination. To solve the constraint system, we keep iterating the following procedure. We migrate all the functions, all the values in value sets, I mean. After they migrate, some conditions can become true. If they become true, then we transform the candidate edge that they guard into an actual edge. We keep doing this until the graph stops changing, until the system stabilizes. So let's see how this algorithm works in this example. We have 2 vertices with values C4 and C2, but these vertices do not have outgoing solid edges. Then we move on to the next step, check conditions. We have at least one condition that will apply. Can you see it? Try to figure out which condition is true. Well, idy is in C2. That causes 2 candidate edges to become actual edges. So we move them from dashed to solid. And then we have a march of lemmings. They leave C4 here, reach Rx, then move into C1, and finally arrive at C5. So all the nodes, C4, Rx, C1, and C5, they will contain the function fn of y is y, which we call idy. The second condition that asks if idy is in C2 is false. And if we evaluate the first condition again, nothing really changes in this graph. So we are done. And this table on the right has the final solution of our system. We see that, for instance, fn of y is y can be bound to variable x. By the way, can you think about the complexity of this algorithm? Try to figure it out. You can even stop the video before I tell you the answer. We have to evaluate the conditions at most O of n squared times. That's how often each thing can change in the graph. Remember, we have any nodes and any values that could be in their value sets. So the graph can change all of n squared times. Each evaluation forces us to inspect all the triggers, so all of n again. If a trigger is updated, then we will have to update value sets. We might have to update all of n of them, for that's how many value sets we have. And each update is all of n because that means doing set intersections where each set may have size n. So in the end, this naive algorithm is all of n to the 50. That's pretty high, but in practice, this algorithm can be implemented to run in cubic time on the size of the program. For the efficient implementation, see Nielsen's book, page 181. That closes the class on how we solve constraints. Next time, I will talk a bit about some heuristics that we can use to avoid having to do control flow analysis to start with.